Hi all. So today we'll be revising from week 9 to 11. And basically, we'll do questions on questions and the concepts that are required for those questions. So we'll just go through those things for today. Just give me 1 minute and then we'll get started with it. I hope my screen is visible, and we'll start with the adjacency matrix. So whatever question there is and whatever concepts it require, we'll do it with the question itself. So let's start with this question first. We have an adjacency matrix in this question, and there are options given to us about this adjacency matrix and the graph corresponding to this adjacency matrix. So firstly, this is a symmetric matrix. Just 1 second. This is a symmetric matrix. In this question, it has not been specified to you, but if you've it's not really necessary. In what happens in your graph is, if you have a graph like this, and if it's not directed, then the matrix corresponding to this, the adjacency matrix, is a symmetric matrix, right? Because you consider it both ways, kind of. So you put one, if this is vertex 1, vertex 2, so you put on 1 2th entry, you have 1, and on 2 first entry, you have 1 again, right? Both these entries are 1 1 in your uh, adjacency matrix. But symmetric matrices are not generally, they don't, it's not necessary that they'll correspond to a directed graph. But if you've been given a symmetric matrix, you can assume it to be just a to be a matrix of adjacency matrix of a directed graph, of an undirected graph, sorry. This is also an undirected graph, right? This one. So if this is a symmetric matrix. So let's just say this is of a, let's consider it to be corresponding to a graph which is undirected. So the graph here is undirected, and let's just read the options first. The
Ma'am,
first
how do
option
you get to
says,
know it's an undirected one?
that's what I just explained. It's not necessary that it will be an undirected graph, but we are assuming it to be an undirected graph. If it's not mentioned in your, if somewhere in your question, it will be mentioned, but if it's not mentioned and it is a symmetric matrix, for the n term, just assume it to be an undirected graph. Is that okay?
Ma'am, if it is a symmetric matrix, then it is an undirected graph, right?
No, it's not. That's what I was explaining. It's not necessarily an undirected graph, because you can have a directed graph like this, right? Now, if you have these things, so you
Uh,
have this graph, V1, V2, V3, and somewhere here
uh,
you have
yeah,
V4.
if it is symmetric around diagonal, we have learned that that is undirected graph.
What?
For the exam,
If
we can
it is
consider it as undirected, right?
Yeah, this is, if it goes both ways, you can consider it to be undirected, but it has been, the directions have been given to you, right? So you
like in
won't
the
be asked
lectures,
such things anymore.
yeah,
Yeah.
okay. In the lectures, it was described that if the symmetric is matrix, I mean, if the matrix is symmetric around the diagonals, then it is called undirected.
Okay. If it's mentioned there, then you can consider, then you can consider it obviously to be an undirected graph. So all in all, this is a symmetric matrix. You can consider it to be corresponding to an undirected graph. Let's
Because there is a
read the
zero, ma'am,
options.
in the diagonal. That's why. Zero in the diagonal. That's why.
No, no, this is a symmetric
No,
matrix.
the other
That's why.
element.
The other elements are, this thing is there. Aij is the same as Aji or all Ij. So because this is true, that means your matrix is a symmetric matrix. That's why this is, and we are considering this graph to be an undirected graph. Not because of diagonal entries are obviously always zero. In directed one also it's zero. Okay. coming to the options, the first option is about the number of vertices in G of degree 3 are 3. So number of vertices of degree, and because it's an undirected graph, so the degree, there's no concept of in degree and out degree, there's only a concept of degree here. So degree 3 is basically, you can just check it from the row or column, because it's a symmetric matrix, so it doesn't matter. So let's just check it from the rows. So there are three non-zero entries here, right? Number of non-zero entries in every row gives you the degree. It adds to the degree, right? So if there's 1, then 1 degree is added to the vertex A. If there's 1 more, then 1 more degree is added, and if there's 1 more, then 3 degrees are there. So the degree of A is 3, right? Degree of A is 3. Now you can check it from row or column, doesn't matter, because it's a symmetric graph. Then for B, the degree for B is also 3. Degree
Ma'am,
of C
how it is 3,
is
ma'am?
2. There are 3 non-zero entries, right? You have to check the number of non-zero entries in row or column in the case of undirected graph. In case of directed graph, you will be asked in terms of in degree and out degree. That's a different topic. Degree of C, I hope this is clear to everyone why we're taking these degrees to be 3D. This should be
Yes,
clear
ma'am.
from here.
Yes, ma'am.
Yes, ma'am.
This degree of C is 2. Then degree of E is also 2. D is 2. And then the degree of next vertex, E is 4.
Oh,
So there are only 2 vertices whose degree is 3. So first should be incorrect. Then coming to the second one, the total number of edges in G are 7. So there are only 5. Okay, they're talking about edges. So about edges, you can count the number of non-zero entries in just up. Okay, because we know that this above this diagonal, if we'll consider the either you consider the entries, the non-zero entries above this diagonal or below this diagonal, right? You can choose whatever way, because it's a symmetric matrix. If there is a non-zero entry here, then you will see a corresponding non-zero entry here. For this one, you have it here. So for every non-zero entry here, don't count it twice. That's what I mean. Just count it once. So it's 1, 2, 3, 4, 5, 6, 7. The number of edges is indeed 7, because there are number of non-zero entries above the diagonal are 7. So this should be correct. This fine?
yes.
And the total number of edges, this can't be 14, obviously. And then there is a cycle in G. So it's actually better to detect cycles. It's better to draw the graph, because it's difficult from here. Let's draw the graph only. I have 5 vertices. A has an edge with B, with D, and with E.
B to C, B to E.
And then C
C
has
to
it.
E.
Okay. C to E is also there. Let's draw it this way then.
Ma'am, everything is connected to E.
Done, right? This is the total graph, right? The
Yes.
overall graph.
Yes,
Okay.
ma'am.
So, and for detecting the cycles, now because you don't have any directions here, so these will be cycles. These will be considered cycle only. In an undirected graph, everything that looks closed is a cycle. And in a directed graph, you consider these arrows too. So this will be a cycle, but this won't be a cycle. But since there are no directions here, so it has cycles, right? This is also a cycle, this is also a cycle, this one's also a cycle. This option should be correct then. Can we move to the next question if this one's clear?
Yes,
Ma'am,
ma'am.
the first option, the
Yes,
number of
ma'am.
vertices are 13, ma'am.
Where?
The number of vertices in this is 13.
Talking
A
It's
to E,
5.
5. How about 13? It's in the question.
Okay, the number of vertices is just 5, right? The vertices are A, B, C, D, E.
No, ma'am, the first option, the number of vertices in G of degree 3 are 3. That.
Yeah, we have written the degree of all of these vertices, right? Degree of A is 3, degree of B is 3, degree of C. So only 2 vertices have degree 3. But this option says that there are 3 vertices with degree 3, which is not true. That's why it's incorrect.
Okay, ma'am.
Okay. Does anyone have any doubt in how to find an adjacency matrix for a graph and all of
So,
those
ma'am,
things?
like, is it
Yeah.
a symmetric matrix? So here the formula for the edges n into n minus 1 divided by 2 is not applicable.
It's okay. That is the maximum number of edges, the one you're talking about, right? The n minus 1 thing you're talking about. That's the maximum number of edges that you can have when you have n number of vertices. So with n number of vertices, this is the maximum number of edges you can have in an undirected graph, right? But we are not talking about the maximum number of edges. This question is about the number of edges in the graph, in this graph. Now, with 5 vertices, you can have maximum number of edges you can have is this A, E, C, D, and E. So E is connected to everything, then B is also connected to everything, then A is also connected to everything, right? But in this case, A is not connected to everything, right? It's different. The n minus 1 formula only works when you have all the possible edges that could be there in the graph. So if you have all those edges, then you use that formula. Is that
For
okay?
undirected graph only, na ma'am. That formula
Yeah,
is.
the n minus 1 by 2 is for undirected one, n minus 1 is for directed one.
Okay, ma'am,
Ma'am,
got it.
why option B is incorrect?
Option B is correct. I've marked it correct.
Okay, ma'am. Sorry.
Okay. Can we move to the next question now?
Yes, ma'am.
Okay, this is the next question. And before discussing this question, should we also discuss the BFS tree? Quickly discuss how do we make a BFS tree, a DFS tree, and then come to this question.
Yes, ma'am, we
Ma'am,
can.
is this a BFS tree or a DFS tree which is given in the question?
This is BFS.
Okay, ma'am.
Okay. So to make a BFS tree, when you have been given a graph, the BFS approaches, you first take the vertex that you start your search with. So if you're starting your search from the vertex V1 or let's say V7, let's start from V1 only. If you're starting it from V1, then you write all the vertices here that are directly connected to V1 and they're considered to be on level 0. This is considered level 1 actually. Directly connected ones are considered on level 1, but this is not of importance. The level numbers are not of importance. So everything that's directly connected to V1, you write them here on this level, and then everything that's directly connected to these vertices, you write them here one by one. So you start with this vertex, then get done with this. Let's do a small example. So if you have V1,
Ma'am,
V2,
the option A would be right, ma'am?
yeah, we'll come to that. Let's just do this thing first. Let's say you have this thing, and then you have to make a BFS tree. So if you're starting your search with V1, it goes like this: V1, then you go to V2, and there's no more vertices directly connected to V1. So we're done for this level. Then for the next level, you scan V2, and there are 2 directly connected to it. So this will be this V3 and V4. But if you start your search from V2, then it will be different. From V2, you will have V1, V3, and V4 all on the same level. And the set search ends on this level only. Now, if you start it with, 1 second. If you start it from V3, then you will have V2, V4 on your first level. And then here you will have V1. That's how your BFS search works. Now coming to this tree again.
Ma'am, when we start for V2, V3 and V4 also we have to connect, ma'am.
Yeah, they're all on first level because they're all directly connected to V2.
So there is a unidirection through V3 and V4 also, ma'am. We have to connect V3 and V4 also here.
So you don't connect, you don't have cycle in trees. So you're because you're making a BFS tree, this edge will create a cycle here. That's why you can't have this thing. Is it okay?
Okay, ma'am.
Okay. Then coming to these options, the first option is, can AD be an edge? So if you look at AD, if AD was an edge in your, if that went edge in your original graph, then you'll have D here, right? Because first you write all the vertices that are directly connected to A. And if D is directly connected to A, you should be writing D here. And if you write D here, because you don't write vertices again in your tree, then your D shouldn't be here. And this thing should not have been here, and this should have been the tree, right? But that's not the case. That means AD cannot be an edge. So this is not an edge. Then coming to EC, EC is this. Now this creates a cycle here, and trees do not have cycles. This is cycle, right? This thing. So that's why this cannot be an edge. EC. And then let's then we have DG. DG has the same problem, and BF has the same problem too.
Ma'am, in the
That
original
means,
graph, it can be edge, right? EC can be an edge in the original graph.
oh yeah, we were talking about, I thought, sorry, I was thinking about something else.
It is BFS.
It's a BFS thing. So this, yeah, EC can be an edge because we're talking about the original graph, right? So yeah, EC can be an edge in your original graph. Your BF can also be an edge, and then DG can also be an edge
Ma'am,
in the
why?
original graph. Because we're talking about original graph, right? This in the tree they cannot be an edge, but if we have a graph corresponding to this, what we mean by this is you can have something like this. You can have A, B, F, and then C, E, C, and D, G. Now that's possible. If this is your original graph, then the graph the tree corresponding to this BFS tree would be this, right? If this is the original graph, then this is the tree, BFS tree corresponding to it. That means these edges are possible in the original graph. We're talking about the original graph, not talking about the tree. Obviously, these are not edges in the tree, obviously.
Yeah, I got confused because you've taken the V1, V2, V3, V4 graph in which V3 and V4 were same like of E and C.
Yeah, that we were here. We were talking about. We were in these cases. We were talking about the tree, not because tree is it. It is supposed to be. It should not have any cycles. That's why you cannot have V3, V4 here. But in your original graph, you can have V3, V4.
But how did you construct that original graph? I am not clear with the part.
We're not constructing an original graph because we don't know what the original graph would look like. It could look like this, or it could look like this too. That could also be an original graph for this BFS tree. It could also look like this, and it could also look like this. So there's no unique original graph to this.
So on what basis actually we are actually considering A and D, because they are talking about an edge in the original graph. If I do not know what is the original graph, so how will I decide whether A comma D is the one which is not the part of it?
AD was an edge, let's say, if AD was an edge in the original graph, then while making the BFS tree, wouldn't you be writing AD here on the first level? Right?
True.
Then you wouldn't write it on the last level. So this tree is not corresponding to this graph. That's why this cannot be the original graph.
Madam, can we have the F and C as an edge? Possible, right?
F and C. See, if you're talking about F and C, it's because you scanning it here first, and then even if C is under F, it's already, yeah. So this can be an edge, but yeah, this is possible in original graph. We're talking about the original graph.
Yes, madam.
So, ma'am, only A option is right now.
Yeah. Which
Ma'am,
cannot be an edge. Yeah, only this cannot be an edge.
Ma'am, last time also you said that from the left there can be an edge. It's completely fine. From left there can be edge in the next level in a way. Is it fine? Is it?
See, this one, because there's some, it depends on how you're doing. If you're making this tree as per your, I don't want to confuse you into the left right thing here. What we did here was, let's just say you had A dash here, some vertex A dash, and then you have been asked, can this be an edge or can this be an edge in your original graph? So we had different rules for this, which holds when you make this BFS tree as per your BFS search. What do I mean by that? That means if you have A and then you're doing things as per this, so as per your, you draw a stack first, right? You start with A, and then if in the stack you mention B first. So if you're drawing this tree and then you mention C, so you should be doing this, right? While making a tree. So if you are making this tree as exactly as per this stack or as per your BFS search, then it's fine. Then this left-right logic that I gave there works. But if this is not exactly per this stack, that means if in the stack you write BC, but in your tree you write CB.
Ma'am, don't we use Q in the BFS?
Yeah, the Q thing. Sorry about that. We use the Q, right? So if you're not doing this, you're not making your tree as per your Q or as per your BFS search, then this left-right thing does not hold. That means you can have this left edge to right edge to both work. And you will not have an option like that. I understand the confusion. That's why we won't have a question like that in exam. Won't have a question like that. By that I mean you won't have these edges.
Ma'am,
So
you
you have
said
to,
like if we are making by the Q, then it doesn't matter. The last point you said.
okay, last time we spoke about this thing, I said that AC, if you have this level, A dash is the first element in your level, then AC cannot be an edge, because if AC were an edge in your original graph, then you will be drawing this under C, right? We discussed this last time when we discussed this entire tree thing. I remember discussing this thing in the class. So that would mean, now that would mean that AC cannot be edge as per. So if you're drawing things according to your Q, that means if you say, and by Q I mean if you're doing it as per search. So if you're assuming that A dash got discovered first, and then B got discovered, and then F got discovered in this order, then you should be mentioning C under A dash, right?
Yes, ma'am.
But if you're not going as per this direct order, that A dash got discovered first, if this thing A dash, your tree has this, right? You have A dash B F. So if this thing, this ordering is not as per the discovery of vertices from A, right? Let's say A dash, we don't know that A dash got discovered first. If this could also mean that B got discovered first, then F got discovered, and then A dash got discovered, but we wrote it in any order. That means we're not following an order on the same level. Then A and C can be an edge in the original graph. And I know that this is confusing. That's why we don't have a question like that, where you have to decide A, C thing or C, F thing. So you don't worry about that. I hope both these things are clear.
Yes, madam.
Yes.
Yes, ma'am.
Can we move to the next question? Should we do the DFS one too? In the DFS one, if you have this graph, let's just do the DFS approach for the same one, V1, V2. For the DFS one, you go in the depth first. So this will get covered like this, V1, V2, V3, V4. If you start from V4, then also it will get covered the same way, V4, V3, V2, V1, just in the opposite order, the reverse order. And let's just take some other graph where V5, V6, V7, if you have this
Ma'am,
graph.
what was the last sentence you said? If we go in the reverse order, like V1, V2, V3, V4 is
Yeah,
there,
if you
and
start your search from V4, and your tree, because initially we just had this graph, and if you start your DFS search from V4, then your tree DFS tree would be V4, V3, V2, and V1, right? In this order, in the reverse order. This is V1,
Not
V2, V3, V4.
necessary. It could be V4,
Yeah,
V2,
it could
V1,
be.
and
It
back to
could be, but it can be this too, right? When I say it can, when I mention something, it's obviously one of the options. We know that there can be other options too.
And ma'am,
Okay.
if you would have started from V3, then too, it would be the same.
If you start from V2, you can, now it can obviously be V4, V3, and you can also take V2, V3,
Okay.
V4. It's not possible for me to mention all things. That's why I mention only one. So this, and then V1. No, we don't have a direct edge with V,
V2 to V4.
right? Just 1 second. We started with V2, then V4, V3. Okay. One way is V2, V3, and then V4, and then tracing back to V3 and then coming here. V2, V3, V4, then tracing back, because we're just considering this graph, V3, V2, and then this.
From V2 to V1.
Yeah, this one way is this. Then the other way could be if you're starting from V2, it would give the same thing. You can go to V4, then V3, and you can do V1 here.
Okay, ma'am.
Okay. And if you're considering this whole graph, and you start your search from, let's say, V3, then you will have V5, V7. You'll go back to V5 because V7 is, okay, you have V6 too here.
V6.
V6 here. Then you will start tracing back to V7, V5, V3. And then from V3, you will have V4, V2, V1. Is this okay?
Yes, sir.
Okay. Then coming to this one, this question is based on minimum cost spanning tree. And the method has not been, because both the methods give the same cost only. That's why the method is not important here. So let's just discuss the methods first, one by one. First is your Prim's algorithm. The second one is Kruskal. So let's start with Prim's algorithm first. The Prim's algorithm search starts with one vertex. Let's say you're starting it with, the last time we discussed it, I said just choose the least weight edge, right? But your
Yes, ma'am.
Prim's algorithm, okay. It's like you can be given in questions, or sometimes actually it happens like that only. You're given the vertex with which you need to start the Prim's algorithm. So let's say you've been given A, then you have to start with an edge which is least weight edge, and it involves A. So from A you have two edges, 4 and 8. So you have to, because you're starting a Prim's algorithm from A vertex. So you should be choosing the minimum of these two, not the minimum of the entire thing. So you start with the minimum this.
Ma'am, you said that
Yeah, last time when we discussed this thing, we didn't discuss it with a vertex.
no, ma'am,
We
you
didn't.
said that least weightage. What was that?
Least weight vertex is
Wait for the edge.
yeah, the least weight edge you have to select from A. So if you have, let's say in your graph, you have these edges from A, B, C, and D. Then you have to select the minimum out of these and then draw that edge. To draw the Prim's algorithm minimum cost spanning tree using Prim's algorithm. We're trying to find minimum cost spanning tree using Prim's algorithm. That's what we're doing here. So the first thing you do is you're always given a vertex to start with. Let's say the vertex given is A. Write that vertex, and then write the next vertex to be the one that's directly connected to A and that has the least weight edge with A. So out of all the edges from A, you have to choose the least weight edge. Even if there's something, even if you have one here, just choose this one. Start with this one.
Ma'am, so from every vertex we reach, we choose the path which has the least weight.
Yeah.
Okay, thank you.
No,
You
if the
start from,
starting vertex is not given and mentioned in the question, then we can
yeah, then you
minimum
can
weight
choose,
vertex.
yeah, then you can choose the minimum one. So let's say in this question, because it's not given to you, if it is given to be A, if your starting vertex to be is given to be A, and you have to perform Prim's algorithm, or you, so what you do is first you add this weight, and next up you add the next minimum one, which is, or let's just do it because it's not given to you. So let's just do it. Let's just start it from C vertex, because vertex is always given in Prim's algorithm. So
And ma'am,
let's
can
start with this
this was
vertex.
written in the question? We have to apply Prince or
No, it's not written
uh,
in the question, but because I am trying to explain both the algorithms here, that's why I'm doing this question by both algorithms.
so how we find in exam that which algorithm we have to perform?
You can use any, that's what I said at the very start of this question. Both of the algorithms are going to give you the same minimum cost. Minimum cost would be same using both algorithms. Your fees can differ, but cost will remain same.
No, but
Is that
why did you
okay?
start from A particularly? We can start from any vertex. Is it given in the question that we
It's
have?
given in the
Okay,
question.
ma'am. Okay,
In
ma'am.
Prim's algorithm, it's given in the question. And if you want to perform Prim's algorithm, but it's not given in the question, then just choose uh, this C one, because this is the least weight, right? So just on your own, choose the one with minimum, the least weight edge you can choose on your own. So I've chosen this one, CD1,
And
I've
we are
chosen.
given the minimum edges CD. So in this case, would we choose C or D?
You choose C. You don't
You
have to
can
write
choose
this thing.
either.
C is the vertex, or you're starting your search, you're starting this algorithm from C. You don't have to write that thing. I just said this thing because
Okay,
Prim's
ma'am.
algorithm generally starts with a vertex. That's why I mentioned that thing. But if you're not given which algorithm to use, but you still want to use Prim's algorithm, then start with the least edge weight, least weight edge. Is
Okay,
that
ma'am.
okay? So start with CD. And let's say in your question, you're being, so you'll be in question, what would you be given? You would be given the vertex as C or D.
Ma'am, can you solve this question?
Yeah, and that's what I'm doing. CD. So you take CD first. Then next, because this, then you can take this edge. This has already been considered, this edge and this edge. And then this one, and this one. So you have to choose the minimum out of these ones. And the minimum is this, right? This is the minimum one. So next you draw this one. And then when you draw this one, because you have reached this vertex, you've covered, this vertex you've covered, and now this vertex is also in your graph. That means you have to choose the minimum weight edge out of these ones. This one, this one, this one. This is already done, right? This is also already done. So out of these two, these three, and then these two also get unlocked, right? So out of these two, too. So out of the marked ones, you have to choose the minimum, and the minimum is, I guess, this one. The next edge you draw is this one. And then because you've unlocked this vertex too, now you can take, you can cover this edge too. So now you have to choose the minimum from these edges, 1, 2, 3, 4, these edges that have been marked. And the minimum is this one, right? DE is the minimum. So you choose E then.
Can we not take edges of F after taking all the edge of C?
After what?
Like after we have taken C, D, C, F, C, A, and D, G also, then can we do the edges associated with vertex E? Oh, sorry, F.
We are considering the edges related to F, right? But they are not, they don't have the minimum
They're
weight.
high right
That's why
now.
we are not, yeah. This is 8, 7, 9. And we have edges with lesser weight than that. That's why we're choosing those edges. Out of the chosen ones, out of the unlocked edges, you have to choose the edges with minimum weight and the ones that do not form a cycle. There are only two rules: minimum weight and no cycles.
Ma'am, no cycle as in, for example?
As in, let's say, okay, let's do this question and you will come to know what I mean. So we were on this one, right? So now E is written, that means E is also covered now. And now you have to choose the minimum weight and 6 is done, right? So you can remove this one because 6 is already, no, 6 is not done, 5 is done. So because this edge is done, so you can remove this. Now you have to choose the minimum from the already taken ones, and this is the new unlocked edge. So this is 10, 6. So now the minimum is this one, right? 6, 1.
6 is a cycle now. But then it will
And this
create
is
a
a
cycle.
cycle. Now if you draw this edge, now as per your search, you should be using EG here because the minimum weight is 6, which is of EG. But you can't draw this here because then it won't be a tree. And we're trying to make minimum cost spanning tree. And trees do not have cycles, so you should not have a closing edge here. An edge that closes a cycle, you should not have such an edge in your tree. That's why you don't consider this minimum. You take the next minimum after 6. So after 6, you have 7, I guess. So you should be,
And we'll
but
also
that's
make a
also closing.
So again, a
This
cycle.
one's also closing. Yeah, that's also a problem. That's why we don't consider this too. Let's come to the next minimum. It's this one, right? If
DF or AC.
AC is also 8. So both of them are fine. You can use AC too. That's also fine because it's not making a cycle. And this is also fine. DF is also fine. And actually, you will have to do this. Okay. So don't draw both,
One of them.
just one of them. If you're going with this one, if you're choosing this edge, then because this vertex gets covered in the tree, that means this edge gets unlocked and this edge is done, right? So now you have to choose the minimum out of these. And the minimum is now 4. So you'll have to draw this edge then. And then the next minimum is now because every edge has been covered. So you can just take the edges with minimum weights now. After 4, you have which ones left now?
Finished. And all the edges of vertex are
And are we done with all vertices? Yeah, but yeah, because no vertices are left, you know that your tree has been completed. A spanning tree has been completed. What do we mean by spanning tree? Spanning tree is a tree that covers that it's a tree and it covers every edge. That's a spanning tree, right? So for this graph, a spanning tree would be a tree that covers every vertex of this graph. And because every vertex has been covered, that means it's a spanning tree. So done with your spanning tree. And obviously, we've performed Prim's algorithm. So this is the minimum cost spanning tree. Is the Prim's algorithm clear to everyone? Each time you unlock,
Yes, ma'am.
write a vertex here, just unlock the edges that are directly connected to it and choose the minimum weight edge in your tree. But make sure that it's not a closing edge to any cycle. There should be no cycles in your tree. That's all. And then for the minimum cost, you can just add these. This is 5.
23.
Yeah. Just add these weights and you will get the answer. And coming to the Prim's
Ma'am, we have to add them and we got the answer 23, like 4 plus 2 plus 8 plus 1 plus
yeah,
5.
just add all of them. And coming to Kruskal's algorithm. In Kruskal algorithm, you just have to, there's no starting vertex. You just have to write the edge with minimum weight first. This is the minimum weight edge. So you just make this one first. And then you take the next minimum weight edge. So the next minimum weight edges, in this case, it's 2. But let's say if here you had 3 and here you had 2. Now this is not directly connected to this, right?
Yes.
But you still are supposed to draw this edge, even if it's not connected. So draw this and draw all the edges in ascending order of their weights. So ascending order is first this, then second this, then this one, then this one. Draw them in this order and make sure that there are no cycles, because again you're trying to draw a minimum cost tree here. So it should not have any cycles. Let's try to make the tree here as per the original graph.
Ma'am, like the case we have taken, you have taken that 2 3s we have taken. So we'll take any one of the three or
Yeah.
both the three.
Because in this algorithm, you're going in ascending order, right? So if you choose this 3, then you will draw this edge first. And then next, you'll only have to know first this. And then on the third number, you will draw this edge. And do we have other, let's say if this was also 3 and this was also 3. If both of them were 3, then it doesn't matter you draw this edge first or this edge first. Eventually, you'll have to draw both of them, unless they're not forming a cycle.
Okay.
Ma'am, but we also have to first draw that second one, na, because that has minimum weight. Like
Yeah, I was talking when the weight is 3 here. I was talking about that case. Now, if you have 2 here, then obviously you will draw this first. You draw CF first, because this after this the minimum weight is 2. Then you draw this one, because this is the next minimum weight. And after this you draw this one. This is the next minimum weight, so you draw AB. And after 4, you have this one, D and E. After this, we have this EG, but EG, again, it forms a cycle. That's why you can't include EG. Next minimum weight after 5 was 6. So as per Kruskal algorithm, you should have drawn this edge, but we're not drawing it because it's forming a cycle. That's why we are avoiding this edge in our tree. And then after 6, you have this one, right? But you can't draw it again. EF edge you can't draw because it's a closing edge for a cycle. So this also we avoid. And then we have these two things, AC or BE. So BF, this one, right? So you can draw them in any order. Both of them have the same weight, 8. But if you will draw now this one, if you will draw 8, then you can't draw this 8 because it's forming a cycle. If you draw this 8 first, then you shouldn't be drawing this one because it forms a cycle. So let's draw this one. And then we're done with all the vertices, right? Because we've covered all vertices A, B, C, E, F, G, right? That means we're done with, and when do you know you're done with the algorithm? When you've covered all the edges, that's when you know that the algorithm is done and you've found your minimum cost spanning tree. Now, if you'll add these ones, you should get 23 only. Yeah, you get 23 only. Adding all of these, you'll get 23. Okay. Shall we move on to the next question?
I have a doubt in practice assignment.
Yeah, which one?
Yep. PA 11 number, madam. The question number 3.
Practice assignment 11,
Yeah.
question number 3. Okay.
Yes, madam. Week 11, madam. Yeah.
Ma'am, can you start from
Are you talking, okay, is your doubt related to the infinity is at diagonal or is it something else?
But my doubt is like how to find, let's say, distance between the two vertices using Floyd-Warshall algorithm. Suppose in that question it says we have to find SP4 or SP5.
Yeah.
So what is the procedure like? We have to multiply, let's say, A square into A3, then we have to kind of, keep on multiplying the matrix multiplication, or is there any other quicker way to reach to the answer?
So we discussed the Floyd-Warshall method, right? Where we said that you have to insert each vertex. So if you have vertices, if you have three vertices, or let's say you have three vertices. In the question, it's different, but let's say in your graph you have three vertices. Then you draw three matrices. Either you denote it by A0, A1, A2,
Yes.
A3, or you denote them by SP0, SP1, SP2, these things. So this was when you insert the first vertex in between every vertex, right? This was your usual adjacency matrix. And then this was, yeah. And this was when you have, so your ijth entry would be 1. If you have I to 1 and 1 to j. Or it was not about 1 because there are weights here too, right? So you used to take these weights. If you have, let's say you have weight 4 here and 3 here, then you will be taking aij as 7, right? Okay, wait.
Yes, madam.
Let me just give you the exact algorithm. We've given a form. What's your doubt? We have a formula for that, right?
Yes, madam. My doubt is like if you see that question actually, number 3, it says if we perform the Floyd-Warshall algorithm for the graph, we have to find SP4, okay, A to the power 4. So like my doubt is, should we, let's say, keep on writing A, then we should find A2, and then again multiply A2 with A2 the way we multiply for matrix, or any other shorter way is there to check whether we can check the options?
But we didn't use to multiply things here, right? We used to, okay. In Floyd-Warshall method, we had a formula that if you're starting with, if you have these vertices and you have to find SP4, then you first find SP1 using this as the intermediate vertex. Then you find SP2 using this as the intermediate vertex. And this matrix has to be, okay, what you do is your formula is this. A, I, J is the minimum of, for if you have 2 here, then you'll have minimum of A1, ij, you use the previous matrix, right? So you use SP1 for constructing SP2. For SP2, you will use SP3. For SP3, you will use SP4, right? Sorry, for SP4, you will use SP3. So you have to construct SP4 in that order. Is that okay?
Yeah, we have to go in sequence.
This order.
Will that not be taking time, madam? Because if you have to find, let's say, SP5
We
or
don't have
SP4,
anything like that in exam. Don't worry. We don't have such tedious things in exam.
because I saw in the practice assignment, so it was slightly time taking.
Okay. Can we move to the next question?
Ma'am,
Yes,
I
sir.
have a query.
Yeah.
Ma'am, in the previous one, if we started from node A, then will it change the minimum cost spanning tree? Like if a node is given?
It's the minimum cost never changes. So it's like,
it should be the same.
Yeah, it remains the same. You don't have to worry about that. If you're not, the problem with the why you even want to ask if we can, if the minimum cost changes or not, is because you want to make sure that both of the methods work the same way. So it's, you can use either of them, right? So you can use any of them. That's not a problem.
Yes, ma'am.
But if you're
So we
not
can
given the
start from
edge,
any
because in
like
this question, yeah, that's what I'm
if
trying
the
to
edge
tell.
is given, if the vertex is given, then
The minimum cost does not change. Whatever edge is given using both Prim's algorithm and Kruskal's algorithm, your minimum cost is not going to change. But if you have not, it's
Your sequence of edges that you discover will change, but the cost will remain the same.
The cost does not change in both the algorithms, so you don't have to worry about that. I find Kruskal's algorithm easier, but you can just do whatever algorithm you want to go with if it's not mentioned.
Okay, ma'am.
And even if it's mentioned, because you just have to write the answers, right? So you can use the other way too.
Okay.
If you're short on time, if you don't have enough time, you can use the one that you're comfortable with. Okay, then coming to this question.
Okay.
This is a weighted graph, an adjacency matrix for a weighted graph. And then there are 7 vertices. This is the adjacency matrix. And you're supposed to perform Prim's algorithm on this graph. So let's just first draw the graph and then we'll do the Prim's algorithm. And you have to write the order. So if you've been asked the order, then you'll have to. Now the order does change in Prim's algorithm and in the other algorithm. The order of these vertices, the discovery of these vertices does change. We've seen that, right? So let's first draw the graph of this. It's from V1 you have, and then from V2 you have, this one's already done. V4 you have 32. That's it. And then from V3 to V6, we have this thing here, V3, V6. This is
4.
Yeah, this is 4. And then V3 to
V3,
V7,
V7,
we
12.
have 12. And then this is V4 and V2. V4, V2 we are done with. So, and then V4, V5. V4, we have an edge here, V4.
V4, V5 is it?
Wait, isn't this the diagonal entry? This one.
I think V4, V5 is 8.
No, no. V4, V5, the line above it. V4,
Okay,
V5.
Let me just.
Entry with 8 is what you're first of all on is V5 to V4.
Just 1 second.
It's an undirected graph, so if we take V4 to V5 or V5 to V4, it will be same, that is 8, I think.
We were doing V4 vertex, right? So for V4, this is 4th one. And okay, we have 8 here. All right. V4 to V5, it's 8. And then nothing. And then for V5 to V1, 36 we've already written. Then V5 to V4 also we've written.
V6 to V7.
V7 is written. That's the last one.
V5 to V7. We don't have
V6 to V7.
V6 to V7.
Yeah.
Last.
V6 to V7, that's 20.
20.
Okay. Are we done with all edges? 20,
Yes.
20, 4, 12.
Ma'am,
In
that's
the graph,
V6
you made
to
an edge.
V7. You wrote
V5
V5
to
to
V7.
V7.
We have V6 to V7. Okay. And it's 20, right? Okay. This is the graph. And then you have to perform Prim's algorithm from the vertex V1. So the vertex has been given to you, V1. Otherwise, the minimum one is this one. So you should have started with this one, but because your minimum vertex, the vertex to start with is given, so you have to start with this, V1. And the minimum weight edge from V1 is this 24 one, right? So the next in the tree should be V2 with weight 24. Now you have this thing. The unlocked edges are this one, and because you have this vertex done, so it's this one. So you have to choose the minimum from these 3 edges. It's 28. So the next one should be 28 and V7. And because we have to
Ma'am,
keep
the
track
minimum
of,
vertices, like minimum edge is 24, right? V1 to V2.
yeah, 24. That's why we drew this edge first. Okay. So, and because we have to keep track of the order too, so V1 got discovered first, then V2, then V7. And then after V7, because these things gets unlocked, this one, the next one should be 12 and
Should be V3.
these two are already done. So, yeah, V3. Next one is V3 with 12. And with V3, this gets
V6.
unlocked.
V6.
So it should be V6.
And V4.
And then there's
Now
just
V2.
one left, I guess. So it should be this one. Because, yeah, but then it should be this one.
V4 to V5.
V5 should also be done.
Okay, V5 is also left. Yeah, and then because this was not unlocked earlier, this just got unlocked when you wrote V4 here. So then the next one should be V5, this state. So this should be your tree. Every vertex has been covered from V1 to V7. So this is the order in which the vertices gets discovered in your Prim's algorithm or gets written in your Prim's algorithm. And this is the tree and the total, because you have to find the minimum cost spanning, the weight, value, whatever it is. So it's the sum of all of these. So it's 24, 32, 8, 12. This one is 4 and 28. And I think the total will be 108 only. That's all. If this question is clear, can we move to the next one?
Ma'am, from the graph theory, from which part can the questions come? Like maximum probability, from which part the questions can come?
From graph theory, important topics involve topological sorting, and then your your minimum cost spanning trees, and then those things too that we did at the start, where we did not all of that. Then perfect matching.
Like because from the PYQs which I did from
Graph
there,
coloring.
MCST was the most, and then the graph coloring and vertex cover.
Yeah.
Topological
things.
sorting.
Try to focus on these things: topological sorting, minimum
And then
cost
the
spanning tree.
longest paths in
No,
DAGs.
it's not required. Try to
Okay.
focus on these ones.
Could you take vertex cover in the last?
Yeah.
Ma'am, in this question, when we go to the question, ma'am, in the question here, V1 to V5 is 36, ma'am.
Yeah, V1 to V5, we have taken 36.
But ma'am, V5 to V1 is not 36.
V5 is this, right?
It
V5
is
to V1 is
36.
also 36. This.
V1 to V5 is 36 and V5 to V1 is 36.
It's
This
36
is V1 to V5. This is V5 to V1.
Okay, ma'am. Okay,
Mentioned.
just a little
They're
bit.
both 36.
Okay, ma'am.
Yeah, I know it's very congested, the matrix. Okay. Can we move to the next question?
Yes, ma'am.
There's nothing to solve in this one. You just have to know about algorithms. So this is Floyd-Warshall is used for all pairs shortest path. That's what we do in Floyd-Warshall. The end matrix gives you the shortest path from one vertex to every other vertex, not from one vertex, from each vertex to every other vertex, right? So if you have n vertices, then your SPN, the matrix that you get at the end, gives you the shortest path from each vertex to every other vertex. From here, your Aij SPN, ijth entry of SPN gives you the shortest path from I to J or J to I, right? So I to J actually. That's Floyd-Warshall. That means this option because it does give you shortest, so this option should be correct. And coming to the second one, the shortest path problem is not applicable to a graph with negative weights. So negative weight cycles. So with negative weights, you can still find shortest path, but with negative weight cycles, you can't. That means this should be correct too. Then coming to the third one, Bellman-Ford algorithm is used for single source shortest path. This is also true. This Bellman-Ford algorithm you use for single source shortest path means shortest path from a single source. That means that's what we do in Bellman-Ford, right? We pick a source, or we are given a source, and then we try to find the shortest distance of each vertex from that source vertex. That's why we call it a single source shortest
Ma'am,
path algorithm. Yes.
we can't find the shortest path if the graph contains negative weight cycle, na?
Yeah, we can't find the shortest path if negative weight cycles are there. That's why this option is correct. Second one.
Okay.
Okay, then the last one is about Dijkstra. Dijkstra's algorithm is used for all pair shortest path. It's not used for all pair shortest path. It's used for single source shortest path. Dijkstra and Bellman-Ford both are used for for this single source shortest path distance. Oh, shortest path. Can we move to the next question? This is the next one. This does not require you to make or to perform Dijkstra algorithm, or because it's an MCQ. So, but it doesn't require you to perform Bellman-Ford or Dijkstra. You can answer these questions without performing them. The first option is about Dijkstra algorithm can be used to find the shortest path from B because it has negative weight. So you can't use Dijkstra here, right? A lot of negative weights. This is incorrect. Coming to the second one, Bellman-Ford can be used to find the shortest path from B0 to B4. You
Yes,
can
ma'am.
use that if you have negative. Yeah, let's just check for negative cycles first. If there are no negative cycles, then you can use it, but we can't be sure, right?
Ma'am, we have a negative cycle.
Yeah, we do have a negative cycle, and I think it's this one.
Yes, ma'am.
This is a negative cycle. This one, it gives you 10 minus 4. 10 minus 4. Wait, this minus 4 is not there. Minus
Ma'am,
6.
but in the option they have told it from V0 to V4.
Yeah, so
It doesn't matter. If you have one negative cycle,
You
you
will
cannot
go
use.
through the negative cycle even if you're going to V4. So every time it will reduce. Ma'am, it is V1, V6, V5, V4.
this will give you 10 plus 2, 12, and this is 13, right? Minus 13. So you're going to get minus 1. The total weight for this cycle is minus 1. You have a negative weight cycle. That means you can't perform Bellman-Ford algorithm to find the shortest path from a single source. This should be incorrect. And coming to the third one, the weight of the shortest path from V0 to V4 is 1. Now, because you can't use any of there's no way you can, no algorithm you can use here. That means you can't actually find the shortest weight in this one. And then Bellman-Ford algorithm cannot be used to find the shortest path from V0 to V4 because there's a negative cycle in the graph, which is correct. This is the only correct option in this.
Ma'am, what about the third? Why it is wrong?
Because when you have a negative weight cycle, what happens is, we've discussed this earlier too. When you have a negative weight cycle, each time you go through that cycle, you get even lesser weights. So let's say in one iteration, you have 1, 2, 3, 4 weights. Next time you can get 0, 0, 2, 3 weights. Next time you can get minus 10, minus 5, minus 3. So you can keep getting lesser weights each time. So there's no end to it. When you have negative cycles, you keep getting better weights in each iteration. That means you can't find the shortest path.
Because we already got a negative weight from V1 to V, that cycle that you took, V1, V7, V5, and V1.
What?
Remember the
Yeah,
example
the
you gave
weight of that complete cycle is -1.
was negative,
Every
that's
time you
why.
go around it, it will keep going minus.
Yeah. 1 second. From V0 to Yeah, so each time you keep getting lesser weights. That's the problem. That's why you can't perform Bellman-Ford algorithm here. And Dijkstra is already not applicable on this graph because it has negative weights. Bellman-Ford is also not applicable because it has negative cycle, and you have only two algorithms. So this one's incorrect. Okay. Can we move to the next one? Next
Yes, ma'am.
question. Okay. It's this. We've been given a graph with 7 vertices, weighted graph, and then suppose we perform Kruskal's algorithm on the graph G to find the minimum cost spanning tree. Which of the following edges are not added to the minimum cost spanning tree? So let me just check for different questions. If there are any other, yeah, this one's a little different. Let's just do this question first and then we'll come back to the previous one. Because the other one is different. This one is different. Okay, let's do this one only first. V1 here, then from V1 to V2, you have 12. From V2 to V5, you have 18. And to V7, you have 14. And from V2 to V1, this is already covered here. Then V2 to V4, it's 16. Then from
3 to V4,
that's it.
16.
V3 to V4, it's also it's 16, right? This is also 16. V2 to V4, V3 to V4, and then V3 to V6. And V6, what does V6 have? It is connected to the third one and to the last one, right?
V7.
Let's make it here. So V3 to V, it's 4. And we also have one here.
10.
This one is 10. Coming to the fourth one is V4 and V1. Did we miss this one here? Okay.
Yes, ma'am.
Oh,
V4 to
that's
V5
V5.
we have missed.
Wait.
The V4 row we have missed.
Okay. One second. It's from V1 to V2, V3, V4, V5 only. And we've already made V5, right? And this says,
V4 row we have missed.
okay, this is V4. All right. This is V4 row. V4 to V2, we have 16. We've made that. Other one also we've made, I guess. And V4 to V5. V4 to V5, we have 4. And then V4 to
V7.
V7,
6.
6. And then
V4 to
V5. So
V7
we
is
don't.
6.
In the V5 one, V1, V2, V3, V4, we don't have to check. With V7, we have 10. This is 10. And then for V6, V6, V7 is 10. We've already made that. And then are we done with all, right? This is it. We'll draw it clearly. It's like this. V1, V2, V4, V6, V3, and this one,
V4
right?
to V6.
V4 to V6, this one. This is
No, ma'am. V7. V7.
V4, V7.
uh,
Take it from outside.
just one second. We had, let's draw V7 here. We had a 10 here, a 10 here, and then this one, right? V4 to V7, it's 6. This is here. This is your graph, and you have to perform Kruskal's algorithm and check which one of these are not going to be the edges there in your Kruskal's algorithm. So let's just start with the minimum weight edge. It's, I guess, 6. Oh no, 4. This one, V4 and V5. 4.
Ma'am, it's 4.
Yeah, 4. Then next minimum one is this one, V3 to V6. It's also 4. Then next minimum is, I guess, this one, 6, 1, V4 to V7. This is 6. Then next minimum is, we're done till 6, right? Next is, I guess, 10. So V5 to V7 or V5, V6 to V7. We can have this 10. And we can't have this one, right? Because it's forming a cycle. Then after 10, you have this one.
12.
12, 1. So V2 to V1. After 12, you have
16.
we have 14,
14.
right? This one, sorry. This one. 14. And then after 14, we have 16, right? We can't make this 16, only this 16 is possible. And this is the tree. We are done with every V1, V2.
And we cannot make
V3.
V2 to V4. It's making a cycle.
Yes.
Ma'am, I think we should not
Okay,
make
this-
V1 to V7.
This is fine. I think we're done with the search, right? Every vertex has been covered and well, right. So this is, and then you can add these things you have to. So which one is not there? V1, V5 is not there. This is correct. Then V2, V4. V2 and V4 is here. That's also not there. Is also correct. V2, V4 is not there. V2, V4 has weight 16, right? And we don't have any edge that has lesser weight than that. That means we've drawn the tree correct. And V7, V6. V7, V6 is supposed to be, it has 10, right? V7, V6 is 10. Yeah, it should be there in the curve, in the graph. This one. This option is actually incorrect. We have V here. And then V1, V7, we do have an edge here, right? So this can be an edge. So this is incorrect.
Ma'am,
These are the two correct options. Yeah.
Ma'am, but like if we have like same weights, like 2 or 3 edges with the same weights, then there are chances of having like different forms of Kruskal's tree, right? So like
It
we
will
can have
only be a
both
problem
forms.
if you have something like this. If you have a V3, you have weight. If you have to include this one, V2, V3. If you have this thing in your graph and this is, let's say, 1 and both of these are 2, then you can only choose one of these, right? While performing Kruskal. So then you won't be asked questions on this. That if this weight, then this thing won't be V1, V3 can be an edge. This is considered that this can be an edge in your Kruskal, in the tree that you made using Kruskal's algorithm. You won't be
Okay.
given, you
So
won't
we
be
can
given things like that.
Okay.
And the answer to it is, if you've been asked, firstly, you won't be asked. But if there's a question like this, then V1, V3 can be an edge, can be in the tree, minimum cost spanning tree.
Okay, then it would become like complicated for like bigger graphs like this.
What?
it would become like complicated, right, for the bigger graphs like this, because we have 2 16s. Or suppose if we have like 3 4s,
But in
then
our case, both of the 16s are forming cycles. So there's no point considering them.
okay.
Okay. Then can we move to the next question? This one.
Ma'am, the last thing that you said in the in the performing cycle, the 16, what was that?
What?
Ma'am, you said na in 16 there is a performing cycle. What was your point?
Yeah, both the edges with weight 16, this edge and this edge are forming a cycle. If you will draw this thing, now this is a cycle. So you can't draw this edge. If you
Okay,
will draw this edge, that's again a cycle. That's why you can't draw this.
okay.
Ma'am, what is the difference between Prism algorithm and Kruskal's algorithm?
I just explained the entire algorithm here. They're different from each other. In Kruskal algorithm, you draw the edges in ascending order of their weights, irrespective of what edge has been covered yet or not been covered yet. That doesn't matter in Kruskal's algorithm. You just arrange your edges. You draw your edges in ascending order of their weights in Kruskal's algorithm, and you only have to make sure that a cycle is not formed.
Ma'am, but
So
that we also did that in Prism algorithm, right?
In Prim's algorithm, you start firstly you're given a vertex to start with. That's first difference, and then second is you only choose the minimum of the weights of edges that have been unlocked. So if you start your search from V1, then you can't choose. Then you, if you're starting your search from your tree from V1, then you can choose the minimum of only these three edges, 12, 18, and 14. You can't choose the minimum from here because you've started from here. And then when you draw, because your minimum here would be this edge.
Okay, got it, ma'am.
Then you choose the minimum from this one. Then this gets unlocked. These two are already unlocked. So you choose the minimum from 16, 18, 14. Next you draw this one.
Yeah, so in Prism algorithm, we can only choose from the unlocked edges.
Yeah,
the
only from the
minimum
unlocked
weight.
ones. Yeah.
Yeah, okay. And in Kruskal's, we can choose whatever is minimum.
Yes. But just
Ma'am,
make sure that there's no cycle.
Ma'am, can you
Don't
just zoom in
Right.
in this? I just wanted to take a screenshot. Just 1 second, ma'am. Can you just zoom in the answer that you wrote, just the graph and all that? Yeah. Can you zoom in a little? Ma'am, a little zoom in if you can. A little below, ma'am. Yeah, ma'am. Thank you, ma'am. Yes, sir. Okay, ma'am. Thank you.
Okay. Then coming to this question. In this question also, it's based on your minimum cost spanning tree only, but the question asks you to choose the number of to write the number of ways in which you can choose an optimum set. By optimum set, we mean the ways in which you can choose the minimum cost spanning tree. So the answer to this should be, how do you decide how many minimum cost spanning trees? Minimum cost is always unique. Minimum cost spanning trees could be more than one. And how do you know if it's, let's say you're performing, because it's not given which of the algorithms you're performing, so you can just simply take Kruskal's. If you're performing, and even if you use the other one, because it's easier to understand it using this one, that's why I'm using this one. The same logic applies to prims too. So if you start with this one, or you'll go with this edge first, right? Then the next minimum weight is this one, so you'll go with this one, and the next minimum is this one.
No, ma'am. C1,
And
C4.
we can use this one too. We're doing Kruskal's.
T1, C4 is first, right?
Okay, we have another one here. Okay. Thanks. We have another one here. This. Or have we been given anything in the question? Okay, not any, there's nothing. So you can go C1, C4, and this is 1. And the next minimum is this one, 2, and this one, 2. Then the next minimum is this one, 3, and there's no other 3, right? Yeah.
It
Now
is
till
making
this
cycle.
part,
It's
okay, this
making a
is
cycle.
okay. I thought this is not here. This you can't take. Okay, then the next minimum is 4, and 4 is 2 edges are there with weight 4. So one is this one, and the other one is this one, right?
Yes.
Okay. So
The last thing, how did you do that? What was that?
just 1 second. We've started with Kruskals. This was the first one we took. Then second edge, this one, then these two, and so far we've not gotten any cycles. And then at 4, 3 is forming a cycle, so we can't choose that one. And then we take 4. So next up let's take this one, 4. Next 4 also we can consider because, okay, this is forming a cycle.
No, ma'am.
All right.
Cycle.
Okay.
C6 you have to
Okay.
take.
So if you'll, so the idea is till this part there was no problem, but when you're coming to weight 4, you have 2 edges with weight 4, this one and this one, and you can't include both of them together. That means you can only include one, right? Either you'll keep C1, C2 and eliminate C2, C5, or you'll keep C2, C5 or eliminate this and eliminate this one. So if you're, let's say you're choosing this one, that means there are 2 ways to it, right?
C6 is remaining,
2
ma'am.
ways. That means you have 2 ways to do this thing. One is this one, the other one is this one, right? And then we have more to it. We have used an into sign here. If there are other ways also, we would write them here. Okay. Let's go further in the tree. If you've chosen this one, then after 4, we have a 5 here, right? So for 5 also, you have the same problem. Either you can draw this 5 or you can draw this 5. You can't draw both of them in the graph because then it will be a cycle and it would no longer be a spanning tree. So either you can draw this one or this one. That's what adds to into 2. Now how, if you understand and or things, and is associated with multiplication or is associated with addition, then you would know why we've done 2 into 2. But if you're not comfortable with this method, this gives you 4. Directly gives you the number of ways. Then every other edge is just written once. After 5, 6 is there's only one edge with weight 6. That's not a problem. Only one edge with weight 7. That's also not a problem. Only one with 8. So we are not going to have problems there. You cannot have different ways from there, but because these were 2, that's why you have 2 here and 2 here. But if you don't want to go this way, one way to look at it is if you draw this edge, let's say you do this. This was already, no, it wasn't there, right?
It was the C5 from C3.
Okay. This was there and this wasn't there. So one way to look at it is from here you have 2 ways. So if you go by this one, then again in this one you have 2 options. Either you draw this one or you draw this one, right? This one or the same tree but with this branch, right? The same
Yes, ma'am.
thing, but instead of this 5, we're taking this 5 this time. So there are 2 ways. And then from here too, you have 2 ways. C naught, because here also you had 2 ways. Either you take C1, C2, this edge or this edge, right? C2, C5. So instead, if this time you take C1, C3, C4, these ones you will have to take. And then instead of this edge, if you take, this also you will have to take. C1, C3, way 2. Instead of this 4, this edge, if you take this one, C2 to C5, because that also has weight 4, right? You can choose either of them. So if you choose this one this time, then again you have two options from here. This one, this was
C5
also
is already
connected, right?
there.
Ma'am, yeah, ma'am, you have written C5 two
Okay,
times.
okay. So this will be 4. So one other way is this, and then from this way you have two ways again. Either you draw this edge, C6, this is one way, or you draw this edge, C3 to C6, right? So two ways from here, total you'll get 4 ways. That's why I did 2 into 2. 2 ways from here, because out of these two edges you can only choose one, so 2 ways from here. And out of these two, you can only choose one. That's why into 2 here. This was just easier and quicker. If you will try to draw each of them, then it will be 4. Is that okay?
Ma'am, if we
Yes.
had like 3 ways to do it, then we do 3 into 2.
Yeah, if you had 3 ways to do, let's say if you have 3 edges and you could only choose one of them,
Yes.
then you would do 3, right?
Okay. Okay.
If once you choose this, then the cases will proceed, right? Then you'll do multiplication here because you're proceeding with cases. Then the other time you'll do this, then this, right?
Yes, cool.
Is that okay?
Ma'am, can you show the question once?
This is the question.
Okay, ma'am.
Ma'am, can you just zoom in the answer, the trees that you have made?
One second.
A little down, ma'am. Okay, ma'am. Thank you.
Okay.
ये क्या copy कर रहा है?
And then we're done with graph theory questions. This is all that you have to focus on for your exam. And then we have the 9th week, right? In 9th
Ma'am,
week,
what is the total weight here?
the
This
total
graph?
weight will be, this is 1, 2, 3, 4, 8, 10, and 15.
Thank you.
Ma'am, but we have to make the cost minimum, right?
Yeah,
Okay, okay. ma'am.
you have to make the cost minimum, but we have same weight edges, right? So if you add this 4 or that 4, it doesn't matter. The weight will remain same. That's why there are
Okay,
two
ma'am,
ways.
got it.
Okay. Then we have integration, the week 9, that's based on integration and Riemann sum, basically.
I'm just asking one thing from the integration, differentiation, limits, and graph, which is the weightage would be in descending order, like of what you can tell.
Integration,
All the topics from week 1 to 12, the weightage would be.
I don't have the weightage with me. I can give it to you at the end of the session by asking, and I don't have it right now.
Okay, ma'am.
Okay.
Riemann sum is important topic.
Yeah, Riemann sum, please do Riemann sum properly from week 9. And okay, let's come to first, let's just discuss the theory of Riemann week 9, which has maxima minima first. And in maxima minima, you simply have to take the derivative of your function and then you have to equate it to 0. And then for all those points, for all those x's for which you get this equation true, that means for all x such that your f dash x is 0, those are your critical points. And out of those, the maxima minimas are the ones. So let's say you get this at x0 and x1. And at f dash x1 is also 0. Then if this is greater than 0, that means your x0 is a point of maxima, no, minimum. So x0 then will be a point of minima, And if you have f double dash x1 less than 0, then this will be a point of maxima. X1 will be a point of maxima. And if it's 0, f double dash x1 is 0, then your second derivative test fails here. That means you can't conclude from here. Okay. Then coming to after maxima minima, the next topic is, just one second, areas under your under the curves. So let's say you have this thing. Simply, if you have this simple line, then okay, before that, are you guys familiar with the integration? Because integration are just formulas that you'll have to learn. Integration of some basic functions like sin x, cos x, and polynomials and all, you'll have to learn those things. And we've already discussed these things, right? Do we need to discuss the rules here again for integration? Integration, there's only one rule. It's integration by parts.
If there is an important one, please explain.
Let's do Riemann sum first then. Then we'll come to integration. So in Riemann sum, let's say you have what are the things that you're given? One is your function, right? You're given a function. Then you're given an interval, let's say AB, and then you're given the divisions of this interval, right? Division, that means partition, that you call partition, like this. X0 equals A, Xn equals B, and then X1, X2, so on, so on, right? So you're given partition, you're given the function, you're given the interval, and then you have to find the Riemann sum. So there are types of Riemann sum. One is right hand Riemann sum. Then there's left hand Riemann sum. And there's one for the center too. I don't know what it's called, but that's
Midpoint. Midpoint.
Yeah. It has a name, right?
Yes, ma'am. Middle Riemann.
Yeah, middle Riemann sum, in which you use the middle point of the part, this thing. So if you have x1 here, x2 here, so in this interval, you have to take the midpoint of this, which is x1 plus x2 by 2.
Ma'am, in that middle sum Riemanns, in that the limits of the integrals are 0 to n minus 1 or 1 to n?
Okay, we'll explain all of these one by one. In the middle one, if you will take, let's do them one by one. In the right hand Riemann sum, let's say you have been given this function. This is your function. And then you have these ones. So you have to take, in the right hand Riemann sum, you have to take the right end of your partition. So if this is it, if this is one interval, one subinterval, this is second subinterval, this is third and subinterval, then the point that you have to consider, the formula for Riemann sum is this: f x I star and delta xi minus 1, right? Where you take I varying from 0 to not 0, 1. I varying from 1 to n, right? Now, what is this? This is, and you don't have to remember this formula, you just have to remember how it's done. So how do you do it? You just take the length of this interval, which is x1 minus x0, right? This is what we call delta xi. These are the delta xi's here. So you do x1 minus x0, and with this you multiply the point that is in this point is also given to you. This x1 star, the point that you have to take here is a point between x0 and x1, and that is given to you generally. Not generally, it's given always. This point that you have to consider here is also given to you. And then you take the sum of all of these terms. So it's like this: x2 minus x1, and then fx2 star, and then so on, so
x1
on.
star is the middle point between x1 and x0.
Yeah, it's this is the middle point between x0 and x1. This is the middle point between x1 and x2.
Okay.
And then we end this with xn minus 1. And because the middle point we're denoting it with So we should take it as fxn star here. So the formula will become fxi star, and it depends how you denote this thing. So if you, let's say you're denoting it with the fxi, yeah, you're denoting it with delta x1, this as delta x2, then this will be delta xn. This will become fxi star and delta xi, I varying from 1 to n. Okay, this is the compact form, but to find the Riemann sum, you don't need the compact form. You need the simplified form, this form.
This is the right Riemann sum, left one. This one is?
This one is simple Riemann sum. Riemann sum means you multiply the length, this length, with the function's value at any point between in this interval. So this is for the length of this interval, x1 minus x0, and fxi star, where this point x1 star is a point between x1 and x0. That means it's this height, right? If this is your x1 star point, then fx1 star is this height, fx1 star. That's what, let's say you have been given a function x square. Or wait, we'll do one example on this later. This is just Riemann sum because you've not specified the point. Which point are you taking from this? If you have this as partition, x0, x1, x2, and x3, that's it. If this is your partition, then because you've not specified the point, when we say x1 star, we mean a general point in this interval. It could be anywhere. Here, could be anywhere. So either you will be specified this point, which points do you have to take, or you will be given right Riemann sum. So if you have been given right hand Riemann sum, that means this x1 star, the point that you have to take from this interval is this, x1. The point that you have to take from this interval is this one. That means, and the point that you have to take from this interval is this one. So your formula becomes x1 minus x0, fx1, plus x2 minus x1, fx2, and x3 minus x2, fx3. Is this okay? This is for right hand Riemann sum. If this is your partition and f is your function. What do we do for left hand Riemann sum? The interval, this remains same, obviously. The length of interval, this remains same. Here you take fx0. Here you take fx1. Because this time you're taking the left end point for this interval. In right hand Riemann sum, you take the right end point for each interval. In left hand one, you take the left end point for each interval. So for x0 to x1 interval, it will be x0. For x1 to x2 interval, it will be x1. And for this interval, x2 to x3, it will be this. So this will be your left hand Riemann sum. And for the center Riemann, the mid Riemann sum, because these don't change, these remain the same. It will be fxi star, or you can say x0 plus x1 by 2. Then this xi star will be the middle point of this. So in middle Riemann sum, you have the point that you consider is this one, the middle point of this interval, then the middle point of this interval, and then the middle point of this interval. And then you write them here. Is this okay?
Ma'am, the whole concept of Riemann sum is to find the area, na?
Yeah, it's to find the area, but it doesn't give you the area. It gives you, it doesn't give you the area, it just gives you, it doesn't even give you approximation, because approximation is when you take n or something. Now if you'll take this function and then you'll divide this entire thing in one, let's say this is the partition that you're considering, then your area, and this is the point that you're considering. This partition has only one interval, and let's say this is the point that you're considering, x1 star. and this will be fx1 star, this height, right? Then this would mean this area is this. Then the area that you're the middle Riemann sum or this Riemann sum by taking this point would be this one. So you've been asked the area of this, but the area that you will find from here using this partition and this point is this. But if you will keep increasing the number of partitions, if you will, let's say, if you take the number of partitions to be n, and then you tend n to infinity, that means you've taken a lot of partitions here. Simply means you have taken infinite number of partitions here. That will give you the area.
The whole area under the curve, exactly.
Yeah.
So, ma'am, the right hand Riemann sum, left hand Riemann sum, and the center Riemann sum, the most accurate is the center Riemann sum. Is it so? Or because it's like divided by
No,
It
it
depends
depends
on
on
the
number of
curve.
partition.
Depends on the curve. If you want accuracy, just increase the number. If you increase the number of partitions, number of partitions, by that I mean the number of divisions in the partition. So if you take 10 divisions, then your area would be more accurate. If you will take 5, it will be less accurate. If you take 20, it will be even more accurate. That's why we say when we take n tending to infinity, our area is the same as the exact area.
Yes,
End
ma'am,
of the day, this is the approximate area, no? Or accurate.
But this gives, if the area exists, if the integral of that function exists, then this gives you the exact area.
but out of the right,
If it
left, and
exists.
center, the most accurate one is to
It
find.
depends on the function. You can't just predict by left, right. If your function is, just 1 second. Yeah. So it depends on the kind of function you have. If you will do the right thing, it will be this. If you have this curve, and these are the partition, this is the partition that you've taken. If you do the right one, it will be this thing, area, this area. So it will give you more area because this is increasing, right? That's why you're going to get more area, because if it's an increasing function and you're taking right hand Riemann sum, then you're going to get more area than the actual area, right? Because you'll get more area here. Your actual area is under this curve, but the area that you'll get is this. Similarly, here you'll get slightly more. So it depends on the curve that you have. Now, in this case, your Riemann sum is giving more, the right hand Riemann sum is giving more area than the actual area. Left hand, in this particular example, left hand Riemann sum will give you less area than the actual area. Now, which one's closer, right hand one or left hand one, we can't say. Is that okay?
So it
Ma'am,
depends
in the
on the
exam, if
slope
they ask
also.
us to do Riemann sum, but we give the answer based on integral, it could be wrong, right?
Yeah, it can be wrong. See, if you're asked, there are two ways to do things. One is your Riemann sum using the, let's say you've been given 3 or 4, it's divided into this subintervals. Now, if this is your partition and you will use the integral, let's say you have to find the left right hand Riemann sum for fx using this partition. Then that is totally different from the actual area of this function from here to here. It's different. That's why we say that when we increase, if you take n number of partitions and you will approach, if you will make n tend to infinity, then the area would be exactly the same as the area under the curve. Let's say if you have x square, and if you will do fx, so you do this thing, right? Fxi star delta xi, and then you do I varying from 1 to. So because the number of partitions are generally given to you, so you take from I varying. If you have 3 subintervals, then you take I varying from 1 to 3, right? But if you will take it to n, and you will make n tend to infinity. Now there are only two cases. Either the integral is possible for this function. That means you can integrate this function. Not every function is integrable. So if this function is integrable, then the answer, the area you will get from here only. That means the area that you will get from n tending to infinity using Riemann sum will be the same as This is called Riemann integral 2, but that's not in your syllabus. This area would be the same as the actual area that you find by using integrals. But this is only when you take n tends to infinity. If you will take I varying from, like in this example, where is it? In this one, we're taking I varying from 1 to 1 to 3, right? So we're taking I varying from 1 to 3. That's why this won't give you the exact area under curves. So this left-hand Riemann sum will be different from the exact area. Don't try to solve it using integration. Let's do one example on this, and then it will be more clear. Like,
Ma'am, you said Riemann sum and Riemann integrals are same?
no, they're different. And Riemann integral is not in your syllabus. Riemann integral is this thing, where you take n tends to infinity. You don't have to think about this. Gives you the exact area under F. But if you don't take n tends to infinity and instead you take I varying from 1 to say 4 or 3 to a finite number, you're not taking a finite number here. That's why you're getting the exact area. You're not putting a bound on the number of subintervals of the given interval. That's why you get the exact area. But you won't get the exact area if you take from 1 to 3.
So ma'am, like 1 to 3 would be Riemann sum and 1 to infinity would be Riemann integrals.
Yeah, 1 to 3 or 1 to any finite number would just be Riemann sum. Okay, let's do this question. Let's say you have a function x plus 4 by x. Or let's say 3x plus 4 by x. And then you have to find this thing, fx 1 to 4. But you have to use right-hand Riemann sum. And because your interval is 1 to 4, right? So you've also been given the partition. The partition is given as equal, partition this interval into equal subintervals. So 3 equal subintervals, or let's say you've been given 3 equal intervals to divide this into. So all of these things are given to you, will be given to you in questions. How many numbers, how do you have to divide the partition, the interval? What is the interval where you have to find the area? And what do you have to find? The right-hand Riemann sum, right? So let's say your function is this. You have to find from 1 to 4. So you divide it into 3 equal subintervals. So it will be 1 to 2, 2 to 3, and 3 to 4, right? This will be it. And then what's the formula? So you do fx1, because you have to find right-hand Riemann sum. So you should be doing fx2, right? So fx2 and then x2 minus x1. Then fx3, x3 minus x2, and then fx4, x4 minus x3 for right-hand Riemann. This is for right-hand Riemann sum, which is what you have to find here. So your fx2, because this length of each of the subinterval is 1 only, right? 2 minus 1 is 1, 3 minus 2 is also 1. So instead of these things, you can just write 1. That means you can remove these things from here. You can simply do fx2, fx3, and fx4. So what you have to do here is your function was 3x plus 4 by x. And here you have to put your x2 is, okay, why have we put x2 here?
F
Your
of 2,
x2
ma'am.
is,
Because
this is x1, this is x2, this is x3, and this is x4. So you have to put 2 here. So you'll get 3 times 2, which is 6, plus 4 by 6, 4 by
4 by 2.
which is 2 only. So it's 8. This thing will give you 8. This is 8. Then you will put 3 here. So you'll get 3 and 3, 9, plus 4 by 3. And then for this one, you will get 3 times 4, 12, and 4 by 4, 1. So this will be your answer. (20 plus 4 by 3). You can solve this. Is this okay? Is this clear to everyone?
Yes,
Now,
madam.
if you
Yes.
had to find left hand Riemann sum instead, this was for right hand Riemann sum. If you had to find left hand Riemann sum, what would you do? Based on this,
F1
you
plus
can just
F2 plus F3.
from here you can check. It should be fx1, fx2, and fx3, because this time we should be considering the left endpoints of each interval or each subinterval. So this should be for left hand Riemann sum. This should be for right hand Riemann sum.
Will it be given in the question?
What would be given in the question?
That whether we have to find left hand Riemann sum or right hand.
Yeah, all of that would be given. What type of Riemann sum do you have to find? What are the subintervals? What is the interval? What's the function? All of these things will be given.
Okay, thank you.
Okay.
Ma'am, this Riemann sum that you have explained, it's quite easy, but in the question sometimes it becomes a little complicated. There are certain intricacies, complexity in Riemann sum. Can you throw some light on that?
Right. Sometimes what happens is you have been given to take things like you've given things from 0 to 1, let's say, and then you are asked to do 1 by n each time. That's in some question I've seen this thing. So you do 1 by n, because you have to, each interval is of the length 1 by n, right? Each subinterval is of length 1 by n, so it becomes 1 by n. From 0 it becomes directly 1 by n. But if this was the interval, then it will be 1 plus 1 by n, then 1 plus 2 by n, then 1 plus 3 by n, and then so on, right? So here you'll have 1 plus n by n, which will give you 2. This is 1 plus n by n, your last point. Here, if you will do, you'll get 1 by n, 2 by n, so on. This will be n minus 1 by n, and this will be n by n. And then you let's say if you have to find the right hand Riemann sum, you have to take f1 by n. This length is 1 by n. The next length is also 1 by n. But the function's value is to be taken at 2 by n, and so on, right? Till 1 by n, f, because you're doing right hand Riemann sum, so it should end at 1 in this case, right? It should end at the rightmost point of the last subinterval, which is 1. The second last will be 1 by n, f of n minus 1 by n. And then you find these things. You write them. There are, obviously, if you will add these things, because it's a something, 1 by n will be common, and then you'll have something here. This plus this plus this. And you'll have a specific pattern here, which has a specific formula, like sum of first n natural numbers, or sum of these things. That is what you will be given. And for some, if you want, I can give you the formula for arithmetic progression, though it's not in your syllabus, but it helps.
Yes, ma'am, you can give.
So for arithmetic progression, if you've been given 1, or let's say you've been given a, and then you've been given a plus d, a plus 2d, a plus 3d. If this is the pattern, then you see, then you can, for the sum of this, though you won't be given such things because you've not studied the arithmetic progression, but the simple formula for this is for the sum of this thing, the formula is n by 2, 2a plus n minus 1 b. This is the formula. So if you have 1, then you have 3, then you have 5, then you have 7, and so on. And you have to take the sum of these things. Then your n here is, because you don't know in this one, we either we know the number of partitions, right? So if your n is given as 10, then you can use that n here. But if you've not been given that n, then you can simply keep it as n. So you can keep it as n, and then here, this obviously is what you will have to stop this sum somewhere, right? Otherwise, this sum will give you infinity. So if you will take n tending to infinity, this sum is going to give you infinity. And if you will take, let's say you take n equals to 10, then you can put n equals to 10 here. Your first term is 1. So this a is the first term, right? So it's 2 times 1 plus, and the number of terms that you have is 1, 2, and you know that it's 10. So it's 10 minus 1, right? N is number of terms. Yeah.
Ma'am,
So
in the
A
above,
is already written here. N is number of terms here. So if you're adding, let's say you want to add these 4 only, that the number of terms become 4, right? So you take n equals 4 here. So for the sum of 1, 3, 5, 7, you can do 4. N is 4. N is the number of terms. And A is the first term. Your first term is 1. So you can do 2 into 1 plus N is 4. So 4 minus 1 is 3. And this is the difference here. Difference between, because they're in arithmetic progression. So the D here is 2, right? So you can take 2 here. So this will be 2.
We
2
can
plus
use
3,
this
8.
formula for any pattern.
It's not for any pattern. It's for this pattern only, where you have A, then A plus D, then A plus 2D. That means if you have equal difference between each term, this
yes,
and this,
ma'am.
every consecutive term have same difference, then you can use it.
Ma'am, the above thing that you have written, can you explain that of the Riemann sum?
Which one?
Just before this AP sum? Yeah, this one.
This
If you
one.
can explain this one, yeah.
Yeah, so I was saying that 1 by n because is common here, right? So take 1 by n
No, ma'am,
common,
just
and then
before
you'll be
that,
left with,
1 upon n into f1 upon n plus 1 upon n
think,
to f2n. Like, how did you come on that? If you can throw some light on that.
if this is your partition, not this one, this one. If this is your partition, 1 by n, then 2 by n, then 3 by n, then the length of each sub-interval is 1 by n, right? What do? You first write the length of this
Delta is 1 by
sub-interval,
n.
1 by n. Then you do, and if you're trying to find the right-hand Riemann sum in this case, let's say. So first you will take the length of this first interval, 1 by n. Then you take f1 by n because you're trying to find right-hand Riemann sum. So f1 by n, right-hand point you have to consider. Then the length of second interval, that's also 1 by n. Then f2 by n. That's what we've done here. And when you will come to the last interval, so if you keep continuing this thing like this, you will come to the last interval, right? So it will be 1 by n. Again, the length of this interval is also 1 by n. And you have to find the value of the function at the right end point of each interval. So the right end point of this is this. So it should be f1. Is
Yeah,
that
ma'am,
okay?
this is fine, but when the question comes in the Riemann sum, it become complicated. Can we do a question of Riemann sum like that, where it is a little complicated, like 1 upon n, like if it is there in this
Okay.
class? Yeah.
Let me just look for a question then. Just 1 second. Okay, this is one of the questions from your activities. So, oh, you won't see question. There's, okay, let's do this one. So you have to find when n tends, so this is the exact type of question I was talking about. If you've been given from 0 to 2, so in this case, you've been given the interval from 0 to 2, and the sub-intervals are this, 0 to 2 by n. And then you have, for xi, you have 2 times This was x1, so you had 2 by n, 2 times 1 by n. For xi, you have, next up, you'll have 2 by n, and then next up, you'll have 2, 3 by n. So this is 4 by n, next is 6 by n, and so on, right? So here you'll have, this is 2 n by n, and the previous one is 2 times n minus 1 by n. Just before 2, you'll have this. Okay, and then the length of each of these intervals is 2 by n, right? This is also 2 by n, this is also 2 by n, this is also 2 by n. The length is, so you start with 2 by n, and then you can use the right hand Riemann sum or the left hand one, whichever you like, because you ultimately have to take n tending to infinity. So left hand Riemann sum, n tending to infinity, or right hand Riemann sum, n tending to infinity, is going to give you the same value. Let's try it with the right one. You will have 2 by n times f of 2 by n. F of 2 by n is 3, 2 by n, so it's, you'll put 2 by n here, you will get 6 by n plus 1. The next one we'll get, so we have 4 here, so we'll get n, 4 times 3, right? 4 times 3 gives you 12. This will be 12 by n plus 1, and so on, till the function's value at 2, which is 3. Okay, let's take it here. 3 times 2 plus 1, which is 6 plus 1.
You have
And the
take the
previous one will be what?
you have taken the delta xi in a common, no?
Yeah, this one I've taken common. That's why we have a bracket here. So this is 2n minus 1 by n. The previous one will be this plus 1, which is going to give you, let's keep it as this only for now. Because you've done this n number of times, so your 1 is n times, right? N into 1. 1 plus 1 plus 1 n times is n into 1. And then you'll have 6 by n, 12 by n, or in simple words, you'll have 3 times 2 by n, then 4 by n, then 6 by n, right? Is this
Ma'am, how
fine
did
to
this last
everyone?
term come 3 into 2 n minus 1 by n?
Okay, let's just not write it in this way. Let's just, where did this come from? 6 by n. 6 by n we get from here, 3 into 2 by n, right? Here. In place of x, you put 2 by n. This is f2 by n. This is f4 by n. This entire thing is f2 by n, right? So instead of writing it as 6 by n, I can simply write it as 3 into 2 by n, 3 into 4 by n, 3 into 6 by n, and so on, right? So I've taken 3 common, and rest I've done 2 by n, 4 by n, 6 by n. I've added all of them, and in the end, you'll have 2n by n. Is that okay? And n you've gotten from here, 1 plus 1 plus 1 n times. So you've added 1 n number of times, that's why we've got this, n into 1. And here you have 2 by n. So from here you get 2 by n plus, this is 3, and then if anyone has a doubt, they can just ask, because I can't check the chat box and all. Okay, and then this, so we can also take 2 common from here, right? because it will make things easy. That's why we're taking
the
2
last
common.
term
So we can
common.
take 6 by n common, 1 plus 2 plus 3. Now rest will
Yeah,
be
that also you can take common. If you want to take 6 by n common from here, that also you can do. That's also fine. Or you can take n common too from here. And then you can do 1 plus 2 plus 3 plus 4 plus so on, because you've taken 2 by n common till n. And you know how to add these things.
So n comes that n plus 3 into 2 by n. Not that n, actually. In the brackets.
You
Yeah,
took 2n common out now.
yeah, we have this common. This was
In the
2n by
left
n.
hand side, that n plus 3 into 2 by n. That n.
That is for the
The
one.
first n.
Submitting all the ones up.
Which one?
The n at the beginning of the bracket.
In the beginning of the
Yeah.
bracket.
Yes,
This
this
n.
n.
Yeah, this n is, are you talking about this one?
Yes.
It's from here, from all the ones. We've added these
Okay,
ones
ma'am.
n number of times. That's why I've written
Okay,
n
ma'am.
into 1 first and then n.
Okay.
Okay, and then this sum is simply n by 2, 2a. So your a is 1 here, plus n minus 1, which is n minus 1 only, and d is 1. So you have 2 plus n minus 1, which is n plus 1, n by 2. So this is your sum. So this entire sum is this. And then you have 6 by n. So you have 6 by n, n plus 1 by 2 for this sum. 6 by n from here and n from here. And then you have 2 by n here. These two get cancelled. You'll have 12 by n. And these two also get
No, ma'am, there
cancelled.
is a plus between
Okay.
that.
Okay, thanks. We have a plus here. Otherwise, this would be infinity. That's what I was thinking. So this will be okay. Now you'll have 2 plus these two n gets cancelled, and then you have 12 by n square, n plus 1 by 2. This is these and this n gets cancelled. You have 2, 6 by n plus 1, and then you can take n tending to infinity as, you can write this as 2 plus 6, 1 plus 1 by n, and when n tends to infinity, this becomes 2 plus 6, and this tends to 0, right? And n tends to infinity, 1 by n tends to 0. So this becomes 2 plus 6, 8. So our answer is 8.
Ma'am, how it becomes 6n? Yeah, here.
Yeah.
No. Like before, in the same line before, yeah.
We had 12. What do we have here? Initially, we had 12n square, and these two are also not cancelled.
No, we have cancelled n by
This
n.
gets
It
cancelled.
becomes
Okay, then one n is left, right? We had n square here. One n from here got cancelled. We had n into n here. One got cancelled. One got left here. And then this gets cancelled. So we have 6 here. And then n plus 1.
Ma'am, when you were writing the formula of plus plus plus, just above that.
Ma'am, yeah, above that.
Yeah.
This one.
Just ma'am, a little more above, ma'am.
Yeah.
Yeah, ma'am. How this 3 into 2 n minus 1 upon n came, and how does it become 2 n upon n?
Which one? This.
Just above that. That is 3 into 2 on the
This
right
one.
side. Yeah, this one.
Let's just. What I did was I directly substituted 2 by n in the function and wrote it exactly here. Instead, we could have just written it in this form. That would have been just easier if you will write it as 3 2 by n plus 1 plus 3 4 by n plus 1 plus 3 6 by n plus 1. So in that way, you can take 3 common. and you can take 2 by n common too. This is just easier. So you're left with 1 here. From here, you're left with 2, here you're left with 3, and so on, so on. And these ones are also left, right? 1 plus 1 plus 1. So from here, you get n into 1. If you want to go by this rule, then you'll have to take 6 by n common from here, as someone suggested. So
Yeah,
if you're
ma'am.
using this one, take 6 by n common. You have 2 by n here. And then you do n times 1 plus for these ones. And then you do 6, you have 6 by n, 12 by n, and then other ones, you have this thing, 6 by n, 12 by n, and so on, so on. 3 times 2 is 6, right? 6 n minus 1 by n. And then you have 6 n by n, right? So you can take 6 by n common from all of these terms, all of these ones. So from here you will get 2 by n, n times 1, which is n only. And from here you will get 6 by n, 1 plus 2 plus 3 plus so on, till n. So you're getting the same thing that we got earlier. Here also we got the same thing, right? But eventually you'll get, yes.
Yeah, ma'am. So
Yeah.
that you have said three just above that you have wrote
Above
3, yeah, 3, 2,
this
and
one,
minus 1 upon n. This one, yeah,
this one.
yeah.
Yeah.
So this came from,
How are you writing things? You're writing them as 3. The partitions are 1 by n, 2 by n, and so on, so on. Then you have 4 by n. Not 1, we don't have 1 by n, right? 2 by n, 4 by n, 6 by n. And then we have, so if we continue in this manner, this is 2 times 1 by n. This is 2 times 2 by n. If we continue in this manner, the n term will be 2 times n by n. And the one before this would be 2 times n minus 1 by n, right? This is 2 times 1 by n. This is 2 times 2 by n. This is 2 times 3 by n. That means we have a pattern here. We're multiplying 2 by n with 1, then 2, then 3, then 4, then so on, then by n minus 1, then by n, right?
yes, ma'am.
That's how we get this partitioning.
Yeah, ma'am. Ma'am, in the question, once, just if you go to the question, ma'am.
Yeah.
Ma'am, here this I thing, can you throw some light on that? This I 1, 2, 3 till n and x1 star, x I minus 1 and xi, where xi star is 2 into I into n. Just if you can throw some light on that.
Okay,
That
in
is the
this thing
same,
you
na?
have,
2i by n.
it's exactly the same thing that we've done here. You're starting with 2, your general formula for xi is xi star. No, xi only. This is for xi. So general formula for xi is, xi means these ones. X naught, then x1, then x2, these ones. General formula to find this is 2i by n. So for x1, if you have to find this, you put I equals to 1, you get 2 times, you get 2 times 1 by n. Here you put I equals to 2 for x2, so you get 2 times 2 by n. For 3, you put 2 times 3 by n. And for n, xn, because your last one you take xn, right? So you do 2 times n by n. And xn is also given to be 2. So from here you can also see that it's 2. Is that okay?
Yes, ma'am. And xi star is the middle point. It's like, is the range
No,
from
xi
xi.
star in this case, xi star is the point that you have to take. You do this thing, right? x1 minus x naught into fx I star. So the point at which you have to, for right hand Riemann sum, this point is x1. In what we've done so far, we've used right hand Riemann sum. You can also, because if the Riemann integral exists, you have been asked to find the integral. If that exists, then every Riemann sum is going to be same. Every Riemann sum, not every Riemann sum exactly. Every Riemann sum when n tends to infinity is going to be same. So if your integral exists, that means this thing. If you have fx and you have to find this thing, you can simply take this thing. Fx I delta xi I varying from 1 to n. Now this is Riemann sum from for first n for the n intervals, right? If you take n tending to infinity, this is going to be same. Now it doesn't matter what fx xi star what you take, it doesn't matter. So you can take xi star to be anything, the middle point of the intervals or the right end point or the left end point, it doesn't matter.
Okay, ma'am, and
In
this
this case,
x
you can use any Riemann sum. Yeah.
and this xi star is 2 into I into n upon n is the same
It's
thing.
yeah, okay. In this question, I just forgot that it's given. I just didn't see this that this is given here. That means you have to find right hand Riemann sum only. If this is given to you, that your xi is, I thought your xi star is not given in the question. I just saw that it's given. That means it's right hand Riemann sum only. Because these are your partitionings and you have to choose your xi star. So for the first interval, you have to choose 2 times 1 by n. That means you have to choose this endpoint. That means it's the same as right hand Riemann sum, right?
So, ma'am, this I would be 1 here and n would be like how you got to know that I star is right hand Riemann sum like 2 into I upon n. So we'll take n as
N you don't take as anything. That's how you find the integral. If you will take n to be fixed, then you can't find integral. You have to take n tending to infinity. So you don't take n to be anything. N is supposed to vary and increase for you to find the integral. We discussed this thing, right? If you limit this n in this summation, if you limit n, let's say you're limiting it to 1 crore, then also it will just be Riemann sum. It won't give you integral. Then it won't be equal to your integral. So if you have to find the integral, you should be taking n here, and your n should not be bounded. That means your n tends to infinity. Is that okay?
In the question, they're asking what is the value of integral 0 to 2 fx dx.
Yeah. They're asking about the integral. That's why we are taking it n tending to infinity.
Okay.
Is that okay?
ma'am, you said that this xi star is 2I upon n. We have to take it as a right Riemann sum. So how you got to know that is a right Riemann sum? 2 into
Because
I.
this is your x naught. Formula is this, right?
Because I is given 1, 2, 3 to n.
Sorry, what?
I starts from 1. That's all.
You start I from x. What happens is, okay. And you take delta xi here, right? So you have your xi star is in this interval because you're taking your xi star. This is the first point that you take from the first subinterval. So your xi x1 star is the point that you take from first subinterval, and that is given to be 2 into 1 by n. That's given to be 2 by n. And this is also 2 by n. That means from the first interval, you're taking 2 by n as the point. Then from the second interval, you're taking xi x2 star, right? X2 star is given to be 2 times 2 by n. That means it's given to be 4 by n. That's the end point of your second interval. That's why I said that this is the same as right hand Riemann sum. Is that okay now?
Yes, ma'am.
Okay. Is there anything else anyone wants to ask? Can we end the session here? Because I think everything's done from my side. And
Ma'am, I have a doubt. It is in graded assignment 10, question number 5.
Ma'am, just I want to take the screenshot of what you have written. Like if you can zoom in a little, yes.
Ma'am, can you please tell for the Riemann sum only if we know the formula, will that be enough?
Ma'am, a little below.
For what? For the Riemann sum?
For the Riemann sum, if we only remember the formula, will that be enough?
Yeah, that should be enough, right? You just have to use the formula and plug in, but you should know what values are what in the formula. If you've written xi star, you should know what is xi star.
Ma'am, a little
And the
more below.
formula is just enough.
Got it, ma'am.
Ma'am, a little more
Ultimately,
below.
you just have to plug in values. That's it.
Okay.
Excuse me, ma'am.
Thank you.
Thank you,
Ma'am,
ma'am.
can you just like tell me about that doubt?
Which one?
It is in graded assignment 10, question number 5.
And
Just 1
in this
second.
question, was there any need of interval from 0 to 2?
1 second. Question number 5.
I don't get the fourth one. Why option 4 is correct?
Okay, let me just paste the question here. Yeah, someone was asking something else about the Riemann something. Is
Ma'am,
there a
I was
doubt in
asking
the?
that
Yeah.
was there any need of interval from 0 to 2 in that question in previous one?
Yeah, if you will change the interval, the answer would change. It's like finding the area of fx from 0 to in this interval. It's like this. If this is your fx, then it's like finding the area from 0 to 2. Now, if you change this interval, then obviously the answer is going to change.
The infinity is for n, not for the interval.
Yeah, this is basically for the number of partition. If that's your doubt, then n means the number of sub-intervals that you've divided this big interval into. So like in this one, it's 1, 2, 3, 4, 5, 6. So in this case, your n is 6. But when you take n tending to infinity, that means you're dividing it into very, very small partitions with length almost equal to 0. If you will take n tending to infinity, then your length would almost be 0, right? Of each subinterval, the length would be 0 only, right? Approximately 0. It won't be exactly 0, it would be approximately 0. Okay, then coming to this question. Just 1 second. Okay, so this question is on vertex cover and I think perfect matching. So which of the following graphs satisfy the below properties? You want the vertex cover of G to be to have 3 vertices. Vertex cover if is a graph, then you want that graph to have three vertices only. This means you want 3 vertices there, and you want 3 vertices in and then for perfect matching, I guess it's the number of perfect matchings. This is the number of perfect matchings that you get.
I guess that I just don't get that why option 4 is correct, because that vertex cover is for that one would be 2, not 3.
Okay, let me just get the fourth example. Fourth option here. So this is your fourth option. 1 second. This is your fourth option, right? You have this as.
Yeah, ma'am.
So if you try to find the vertex cover means the minimum number of vertices required to cover all the edges, right?
Yeah,
You're saying
that's a CTV. So,
which two vertex cover every other edge?
So I
You
have
try to find
taken
the
like
vertex.
second one. Yeah, I have taken the second vertex and
This
like
one.
this one, yeah, and the other side, second one.
This
Yeah,
one?
this one. Yeah.
Okay. So okay, this covers this one. This edge is covered. This edge is covered. What about this edge? This edge.
If you take the bottom one, it will cover, right? With two vertices only.
No,
Instead
no,
of
ma'am. Ma'am, the above we have taken the above vertices which cover that vertex, right?
If you're
you take
taking
the
1 second, if you're considering this one, then it will be this
No,
covered,
no,
this
no.
covered, but from this edge you don't have anything.
I'm not considering this one. I'm considering
Okay.
that one, which you are
This one?
correct. And yeah, this one. So it will take that first edge, second edge. Yeah, because they are also connected, right? So this one also they are connected. So
When you're trying to find the minimum vertex, the minimum vertex cover, that means you have to find the set of vertices such that from each edge you have at least one vertex, right? Now consider this edge, this edge. You don't have any vertex present from this edge. If you consider, let's just call this one V1, this one V2, this is V3, this is V4, this is V5, and this is V6. Now, if you're choosing V2
now suppose
and V3,
we just implant a CCTV at the position V2 and V3. So it can
have a
yeah.
CCTV
So it
here.
can cover and there. So it can cover like V1, V4,
Hold
and
on a
also
second. You don't have to dictate the entire list of vertices. How would you cover this edge?
Ma'am, we don't
Or
cover
someone
V3. Yeah, V3 on V3 we can like V3 is connected to V5 and V5 V3 is also connected with V6, right? So they covered those vertices are covered by V3.
You don't have to cover vertices, you have to cover edges. You have to cover edges. You have to make sure that if a CCTV is installed here, then this corridor is covered. This corridor is also covered. This corridor is covered. One CCTV is here, so this corridor is covered. This corridor is covered. This corridor is covered. Now, what about these two corridors? This corridor. What about this corridor?
Go for V5.
You will need V5s to cover both of these. That means you have three vertices in your vertex cover.
Yes, sir. Okay.
Okay.
Ma'am? Yeah, actually, ma'am, I took this course of IIT Madras for mathematics only, and I wish to connect with maths teacher. Like, can you share your email ID so that if you can also share me some notes of that or in general, ma'am?
The email ID is on the portal.
Ma'am, of yours, if you can share your email ID.
That's also there on the portal, I guess.
We got a mail saying tomorrow there is a class at 4 o'clock discussing mock, but we didn't get any calendar link.
Okay.
We are yet to get a calendar link in the mail.
Did no one receive a calendar link for tomorrow's mock discussion?
4 to 6, the mail had come, but at least I didn't get any calendar.
Ma'am, can you please explain the perfect matching?
One second,
It's
please.
updated in the calendar. I have it on.
Even in the calendar, the Google calendar, it is not showing me tomorrow that there is a meeting at.
Is it the same for everyone or just
No,
for
it is
this?
update. It is updated.
No, ma'am, I
in
have
the
it in my
calendar.
calendar.
Everyone else has it in your.
Can you please
refresh
place it on your
refresh your calendar?
Refresh your calendar and you see the link there. Must have been uploaded later.
At least I'm refreshing as I speak, but it's not showing. Okay. Can somebody paste a link there in the chat window, please? How do I get it otherwise? If for today's meeting I have, for tomorrow's 4 to 6, I don't have in my Google Calendar.
You can ask in the
Someone has
group
pasted
also.
it, right? Someone's pasted the link in the chat.
Okay, I'll take it. Thank you.
Okay.
Ma'am, can you now explain the perfect matching of this question only?
Okay, the perfect matching.
Yeah, ma'am. I am confused a little on this part.
And this option's been marked correct, right? So the perfect, are you talking about this option only or the other option?
No, ma'am. If you can just in general
Okay.
explain the perfect matching.
So for perfect matching, there has to be 3 perfect matchings, right? So if you will do this thing, B1, how many vertices are there? It's 6, right? So I'm also, because I'm not sure if it asks the number of, if it's asking the number of perfect matchings or, oh, I
No,
think
ma'am,
it's the number, PM is the
it's
perfect
asking
matching.
number of edges in a perfect matching.
Okay, it's about the number of edges always remain the same. Maybe it's asking about the number of perfect matchings in this sense. V1, V3. It's asking about the pairs. So it's asking about the pairs, it has to be 3. If it's asking about the number of perfect matchings in this sense, that V1, V3 could be. So for V1, you have V1 option. Okay. If we look at this graph, let's not erase V1, V2, V2, this is V3, V4, V5, and V6. For perfect matchings, V1 you can take V2 or you can take V4. These are 2 possibilities. Then with the V2, so if you've taken V1, V2 together, you can't take these 2. So if you can take V5, V6 together or V5, V3 together. And then there could be one more way to it, which is V1, V2 and V5, V6. V1, V4. So if we'll follow this order because this option has been marked correct. And then V1, V2 and V5, V4. You can't take V5, V4, right? Because then V6 is left with no choice. V6 also has very limited choices. So either you can have, under this one, you should first discuss V6 because it has limited choices. So V6 can be paired with V5 or V6 can be paired with
V4.
And if it's paired with V6, V5, then V3 is left with no choice. That means V6, V5 can't be paired. That means you should be taking, there is only one possibility for V6. In this case, if if V1 has perfect matching with V2, then V6 should have it with V4 for V3 to have an option, right? Otherwise, V3 is left with no option. One, two, three, four, five, six, right? V1 and V2 are there. V6 and V4 are there. V3 and V5 are there. We're done, right? This is one
Ma'am, can
perfect
we
matching.
say, ma'am, can we say V1, V4, V2, V3, and V5, V6?
Yeah, we're trying to go in a particular order. First, we're fixing this edge. V1, V2, we're fixing, and we're trying to find all the possible ways when these two are fixed. So we discovered that there's only one possible way, right? V1, V2 if you've chosen. Then for V6, you'll have to choose either V5 or V4, but you can't choose V5. So you'll only have to choose V4. And then for V3, so if you've decided this, then the other two already automatically get decided, right? There's no other choice.
So, ma'am, we always fix one edge and calculate the others, right?
To make things easier. Otherwise, you'll get confused. Which one has been done, otherwise you'll end up discovering same things. That's why I'm trying to do it in a systematic order.
Got it, ma'am.
V1,
Got it.
V2 has been done. Then let's come to V1, V4 case. And for V1, V4, there could be several cases. So let's do the first case, which is V1, V4 first, and then with V6 does not have any choice. V4 is not a choice, so you should be taking V6, V5, right? It only had two choices. V4 is already taken, so you should take V5 next. And then V3, V2. That means once you fix V1, V4, the others also get fixed. So if V1, V4 is fixed, there are only these two choices, right? By that logic,
Yeah,
we'll only have two perfect matchings here. Is there any other way to match things here?
No, ma'am. It has only two edges. So you cannot have it.
Okay, that means this is not what the question suggests. Then this has to mean something else. That means it
ma'am,
suggests
so
that.
this graph has two perfect matching, right? Not three.
But I was just trying to make sure that is this what it means? I'm not sure what this thing means. What is this the cardinality of? And it looks like it's the cardinality of the number of so number of perfect matchings are taken to be these things. This is one perfect matching, this is another perfect matching, and this is third perfect matching. So there are three perfect matchings. Now the question that you might see in exam, and similar questions are there in your previous years too, where you have a group divided. Let's say there are four people. There's like group divided here. This is, let's say, grade 10 students, and this is grade 9 students. Let's say there are four students here, four students here, and then you have to choose the mentors for grade 9 students, and they have to be grade 10 students. So let's say you're saying that this person can be mentored to only these two people. This person can be mentored to only this person, and this person can be mentored to these two people, or this person can be mentored to these two people. Then how many such pairings are possible? How many such arrangements are possible? This is what we did here in this case too, right? This is the exact
Yeah,
same thing
ma'am.
that we were doing here. That's what we do here. In this question, what they're asking is, let me just clear this one up first. I believe they're simply asking the number of perfect matchings as this as one perfect matching, this as two perfect matching, and this as three. So obviously there are six vertices and the perfect matching, there could only be three, right? And do you have a perfect matching here? I can also find this here. This is a slightly ambiguous question. So
Ma'am, in two ways we are like finding the perfect matching, right?
yeah, in this example, in this particular example, there are two ways to find the perfect matchings, or two
Okay, ma'am.
arrangements. One is this arrangement, the other one is this arrangement. And coming to this one, if you have something like this, let's call this A1, A2, A3, A4, and this as B1, B2, B3, B4. Then you can try making because A2 can only have B2. It only has one choice. So that one is fixed. And then now this has two choices again, right? This has two choices, but because A2 has only one choice, that means A4 can't be paired with B2. So it will have to be paired with B3. And then B3 is also taken. Okay, let's take this as this. So one possible A2, you just start with the one which has the minimum number of edges. So A2, because it has minimum number of edges, so it only has one choice, B2. And coming to A1, A1 has two choices. We'll come to that later. This is fixed. And for A4, you have three choices again. So the choices for A4 are not fixed now. Let's try to see these things. How many possibilities are there?
The answer would be 4, right?
4, let's just see how many possibilities are there. Let's see. You can map A1 to B1. Let's do A1, B1 case first. And then if A1 is mapped to B1, A2 has no other choice but B2 only. And then A3 has two choices here, but B1 is already taken, so you should only be taking B4. And for A4, because only one vertex is left, so you should be doing it for that one vertex only, which is A4 and B3. Then next up, you can take A1 and B4. If you take A1, B4 this time, A2, B2 is already fixed. A2 does not have any other choice. This time we have taken A1, B3. So we've taken A1, B3, then B1 is available, A2. So A3 can be mapped to B1, right? And A3 has one more choice, which is B4. While keeping these two same. So A3 has these two choices. We've done both. And then A4, if A3, B1 is there, then A4 has to be mapped to
B3.
B2 is done, B3 is left, right? So A4 has to be, but B3 is also done here, right? We started with B3.
A4, B.
B4.
And A4, you'll have to take for B4. B4 is only left. That means you can't have A3, B4. Because when you start with this, A4 has B2 choice. B2 is already taken up by A2 because A2 has no other choice. Then A4 has B3 choice. You started with A1, B3. So you can't take that either. And that only leaves you with one choice for A4, which is B3. Sorry, one choice for B3 is already taken by A1. So it only leaves you with A4, leaves A4 with B4. That means that's the only possibility. That means this case is not possible. You can't, if A3 will take up B4, then A4 does not have a choice. B2 is also taken up by A2. B3 is also taken up by A1. Now, if B4 is also taken up by A3, then you are not left with any choice for A4, right? This case won't be there. I think that these are the only two
Ma'am,
possibilities.
cardinality, number of edges. Whenever they mention cardinality, the number of edges in the perfect matching.
Yeah. We don't, because we try to keep things as clear as possible. So you won't see such things in exam where you can't decide what it actually means.
Ma'am, what is this VCG is equal to 3 means here?
VCG equals to 3 means the number of elements in this. VCG is the vertex cover for your graph. So this is vertex cover for your graph. So this means the number of vertex covers. Not the number of vertex covers. It means the number of elements. Your vertex cover is a set, right? This is a set. Where it's simple because vertex cover is a set, and its cardinality means number of elements in that set. So if this is one of the vertex covers, and every minimum vertex cover that you have, by when someone says vertex cover, it automatically means we're talking about minimum vertex cover, because maximum, so you can take all vertices, right? Maximum vertex cover will be take all the vertices in that set. So when you say vertex cover, we mean minimum vertex cover only. And by the cardinality of minimum vertex cover, we mean the number of vertices in your vertex cover. Cardinality of this set. A perfect matching is also this, right? V1, V3, V1, V2, and V6, V4. So if this is your perfect matching, then the cardinality is 3. So I think this is what this option means. So if you see PM, this thing, that means the number of elements in this set, in your perfect matching set. Is that okay? Is this clear to everyone?
Yes, ma'am.
Yes,
Thank
sir.
you. Thank you.
Okay.
Yes, ma'am.
Yeah, ma'am.
We'll end this
Thank
session
you,
here.
ma'am. Thank you. Thank you for solving my doubt.
Thank you,
you.
ma'am.
Bye, guys.
Thank you so much.
Thank you, ma'am.
Do we have class tomorrow also?
You only have mock discussion tomorrow with the TA
Yeah, but
from
before
4 to
you end,
6.
you actually mentioned about the weightage thing. Is it going to be 9 to 11 or is it going to be equal distribution of weightage given the interim?
9 to 11,
The
I'd say
weightage of
there are obviously more questions from week 9 to 11, but from other weeks you'll also see questions there.
Yep.
I don't have the exact weightage right now.
Okay, thank you. Did they send any email regarding this?
Email regarding what?
Regarding the weightage of the
I don't think so. I think you should see that on your portal.
Okay, thank you.
Okay.
And like we will not have any mock paper discussion the rest, like Saturday or Friday.
You have a mock discussion tomorrow. That's tomorrow from 4 to 6, I guess.
Tomorrow is the last session of math, if I'm right.
Yeah.
Is it not possible to like postpone the session from 6, madam, because 4 to 6?
Oh, it's not possible to shift it to 6 to 8.
Okay. Where to
Thank you.
get the recording for that session, madam? Because I'm a working professional, so
It's in the
difficult.
TA recordings.
Okay.
Where do you guys find TA recordings?
Ma'am, there is a sheet given by TA,
Yeah.
a Google
There's a
sheet, which is, I think, someone can
You'll
paste.
find the recordings there. Or you'll find
Ma'am,
the session, tomorrow's session there in that sheet.
Recordings are also available in the calendar itself.
But for mathematics, it's not available. It's only available for CT.
actually, mathematics TA has made a separate Google sheet for that, and maybe someone can share that link of Google sheet here that you can access it.
Yeah. Can somebody share that sheet?
You can
please?
also access it from the Google Calendar, no?
Yes.
For maths, it's not there. Only for CT, it is there.
No, for maths also it is there.
You have to sync your calendar, I think.
Someone can put the link of that sheet here. Just put it here. Okay, thank you
Ma'am,
guys.
just asking in general,
Yeah.
like, are you PhD in mathematics or like MSc, like in general?
I've done masters in mathematics.
Ma'am, actually,
Not
I
a
wanted to
PhD.
pursue mathematics in masters. Like, if you can guide a little, if you can share your contact or WhatsApp, something like that.
We can discuss this on mail. You have my mail ID, right? So you can
No, ma'am,
discuss
I
that
don't
tomorrow.
have. I don't have. Can you share your mail ID or something?
It must be on the portal. Other IDs, mail IDs of
I don't know, ma'am. If you
the
can share.
instructors not there on the 1 second.
Yeah. So okay.
I think you can just, if there's anything, you can just put it on Discourse because I can't share my personal contacts here. So
No, ma'am, your email ID. I
I
mean,
can't share that either. So
Okay, fine, ma'am. Okay.
thank you. Okay, thank you guys.
Thank you.
Thank you.
Thank you, ma'am.
Madam.